Hey, it's Mr. Celentano, and this is part 2 on our series about atomic theory and the scientists who came up with the theory of atoms. So this is part 2. So up to this point, we talked about Democritus and the BC all the way up through Dalton, right? And the thing that they had in common that we want to focus on is that they all thought that the atom was the smallest particle, right? Atomos, atom, and that it was like an 8-ball, right? It was just like this indestructible particle that didn't have any subatomic particles. They just thought it was this is as small as you could go, essentially, was this 8-ball. What we're going to talk about now is the scientists who discovered, actually, that's not really true. And so the first one we're going to talk about is a guy named J.J. Thomson. So enter Thomson. So Thomson's most famous contribution is that he discovered the electron. That is what he contributed. So like Dalton, most scientists in the 1800s believed that each atom was like a tiny solid ball that could not be broken up into parts. However, J.J. Thomson discovered that was not true. And so this is what his theory was. His theory was actually, if you take the atom, here's the atom in his theory, he said that actually there was a uniformly distributed mass around the atom, so the whole sphere had this mass evenly distributed, and that amongst the atom was placed in these little tiny balls that were electrons, and he thought it was like plum pudding. So if you look at our picture of plum pudding over here, that's what he thought that it was like. That essentially the plums were like the electrons, and they were just floating around inside the atom. So here's our negatively charged electrons and our ball of positive charge. So the most important thing about this is that J.J. Thomson felt that the mass was evenly distributed all around the atom, and that it was all positive, and that's what attracted these negatively charged speckles around the atom. Another name for this was actually the cookie model, the cookie dough model, because the chocolate chips are like electrons and the rest of the cookie is like the rest of the atom. So the way that he did this was by using a cathode ray tube. So the way that he actually discovered the electron was by using a cathode ray tube. The ray tube had already been discovered by a scientist named Crookes, but Thomson essentially used the ray tube to discover these. So what a ray tube essentially is it's a piece of tubing that has most of the air has been evacuated by a vacuum pump. So there's a little bit of air in there. It's very low pressure is one of the most important things, and it's hooked up to an electricity source. And so basically under all this specific scenario, once you run electricity through this tube, that's when you can see what's called the cathode rays. They actually used to use a version of this tube in old-fashioned televisions, the ones with like the kind of the fat backs. Like you probably haven't even seen those anymore. Those were a version of the cathode ray tube. And so here's an example of what we're looking at. So this is actually when you run the electricity through it, here's the ray that's produced. Now, the most important part about what Thomson noticed was that as he was producing this ray, he actually put a couple of magnetic plates around the ray. And so if we look, here's a positively charged plate and here is a negatively charged plate. So this ray is being fired through this tube. It's going from the left, it's all the way to the right. And when he puts the negative plate towards this tube, it's repelled by the negative plate. So this tube does not want anything to do with negatives. And when he puts the positive plate toward it, it's actually attracted to the positive plate. So based on that, that's when Thomson said, wait a minute, there's definitely something here. And whatever it is, it's attracted to the positive and it's repelled by the negative. So because of that, what can you say what must be the charge of the electrons? So the electrons, because of that, he realized are negative. He realized they have to be negative in order for this to make any sense. Okay. So wait, at this point, if atoms have no overall charge, we know the atom has no overall charge, right? And if there are negative parts that make up the atom, then there must also be positive parts, right? What are the positive parts of the atom called again? So those are the protons, and they were actually discovered by a scientist named Goldstein. So Goldstein was the scientist who made the protons. Who discovered them. He didn't make them, of course. He discovered those. So now we have Thomson discovered the electron, and Goldstein discovered the proton. There was also a scientist named Millikan, and he's famous because he found that the quantity of charge in an electron and the mass of the electron is much less than that of a proton. So the mass of one proton is about the same as the mass of 2,000 electrons. So there's a big difference in mass there. So the electrons have a very, very tiny mass. And then there were neutrons also, and they were discovered by James Chadwick. So he was the one who discovered the neutrons, that last subatomic particle that we were talking about that makes up the atom. So here is just a visual on essentially, here's a chart on what that looks like. So as far as the relative charge goes, the electrons have a -1 charge, the protons have a +1 charge, right? Neutrons have no charge, right? For symbols, so you're going to want to know these symbols too. The symbol that scientists use to represent an electron is e to the -1. A proton is p to the plus, and a neutron is n to the 0. So just the letter that it starts with and then the charge basically is how that's represented. The other important part is that the actual mass is very different. So protons and neutrons have essentially very similar mass, but the electron mass, look at that negative exponent, is much smaller. Much, much smaller. It's actually 1/1840th the mass of the other two particles. Okay, so enter Rutherford. So this gold foil experiment is going to be one of the most important things we talk about in the whole unit, so you want to make sure you pay attention to exactly how it works. So essentially, Ernest Rutherford was doing experiments, and he found something that he actually thought was different than the plum pudding model that Thomson said. So these guys actually knew each other, interestingly enough, and Rutherford said, actually, you know what, I think you're wrong. I think that I found something else. So how did he do that? Well, he did something called the gold foil experiment. And so this is the way it worked. So you had a fluorescent screen. So there was a screen placed around this setup, and you had something called an alpha particle launcher. Now, this is a launcher of alpha particles, which are positively charged particles. And so the last piece of it was he had very thin gold foil that he placed here. So the way the experiment went was that he fired alpha particles into the gold foil, and the way that he could actually see these alpha particles, because they're so small essentially, is that they would light up the fluorescent screen behind the gold foil. This way he could actually tell where they went after they went through the gold foil. Now, one of the other most important things is that most of these alpha particles shot straight through the gold foil. These positively charged particles, most of them shot straight through. You can see it over here. They went straight through the screen. But every now and then, one ricocheted. One ricocheted off the gold foil. And so this didn't make sense to Rutherford if he was following Thomson's model, because if Thomson's model was true, then all of the alpha particles would go straight through. There would be no ricochet, because essentially there would be nothing stopping them, because the mass is evenly distributed in J.J. Thomson's model, and so all the particles would go straight through, just like the mass is kind of evenly distributed in this gold foil. But instead what happened was some of them bounced off. Now what this looks like on an atomic level, so if we zoom in, here's the alpha particles. Most of them are going straight through, right? But then some of them bounce off, and because the alpha particles are positively charged, and because they bounced off, that means that whatever they hit must be positively charged, and it must also be very dense, because it's basically making these particles ricochet away from it. And so what Rutherford proposed actually was he discovered the nucleus. He said, no, the atom does not have its mass evenly distributed. In fact, the mass is very concentrated at the very center of the atom. There's a very, very dense core called the nucleus. So that's what Rutherford found. And so let me show you a video of what I'm talking about, because this will help you visualize it.
The nucleus of an atom was first discovered when a beam of positively charged particles emitted from a radioactive source was aimed at a fluorescent screen. The particles caused the fluorescent screen to glow. When a very thin sheet of gold foil was placed in the pathway of the particle beam, a few particles were deflected to the side. Occasionally, particles were deflected straight back. But nearly all particles passed right through the gold foil, as if it were not there. The scientists concluded that atoms must be mostly empty space, and that because some particles are deflected, there must be a small positively charged central mass, which they called the nucleus.
Okay, so the most important things about the video you just watched. One is that there's a nucleus, right? The mass is not evenly distributed. There's a very dense nucleus in the middle that's making these alpha particles deflect off. The other is that the nucleus must be positively charged because the particles themselves are positively charged and they're being deflected. And similar charges repel each other, right? The other thing that made Rutherford's experiment different from Thomson's is that Rutherford said that actually most of the atom is empty space. And Thomson thought that most of the mass was evenly distributed around the atom. So here's a visual of what that looks like. Here's Thomson's model. Here, all this positively charged mass, this pink, is evenly distributed all throughout. It's like a solid ball still with some electrons speckled in there. This is Rutherford's atom. Rutherford's atom says, here's all this empty space around the nucleus, and then here's that dense nucleus right in the middle. So essentially, Thomson felt that it was like this, right? Still kind of a solid ball, but with electrons speckled in there. And Rutherford said, no, this is actually mostly empty space around here, and then here's the thick nucleus, the dense nucleus in the very center. So that's it for this portion of atomic theory. Thank you for watching, and remember, chemistry is everywhere.